once upon a time, people historically started to work with the natural numbers. This here is a capital N where this part is doubled. This is a notation, a symbol for the set of all natural numbers. Set of all natural numbers. And that's 1, 2, 3, and so on. Basically, I like the word natural because physically, the fact that this is not 1 but 2, that's physically out there. They describe something that physically exists in nature. Birds recognize natural numbers. Like if you have a bird and it sits on 4 eggs, but if you steal out 2 eggs, it will recognize that 2 are missing and it will abandon the nest because it's no longer worth the investment of sitting on it. V3, so I like the word natural for these. By the way, that's not universal in my country. 0 was considered to be a natural number, which I now disagree with. A lot of the things I agree with how I learned before I got here, but this one I think America gets it right because historically it took a long time to come up with 0. And until we came up with 0, we were in trouble with decimal place value notation, because how do we communicate that this number is 101 and not 10 plus 1 if we don't have 0? So we were in trouble until we found 0, which took a long time. All right. Now, after we have numbers, we of course have operations. Now, the 4 basic operations are addition, subtraction, multiplication, and division. Now, let me ask you a question. True or false? True or false? The sum of any 2 natural numbers is a natural number. Natural number. So, true or false? If we add 2 natural numbers, that sum is gonna be a natural number for sure.
True.
That is true, indeed. So now imagine that nothing else exists, just the natural numbers. Then the fact that it's a natural number means the answer exists. Now, that's not for difference, right? Can you name a subtraction that the result is not a natural number? But how about 3 minus 10? Right? 3 minus 10 is not a natural number. So if we don't define negative numbers, then 3 minus 10 is an operation with no result. The result doesn't exist within the set. We don't like that. Actually, the fact that the sum of any 2 natural numbers is a natural number, we like that, and we call it closure. So this is true. And one way of saying that is that the set of all natural numbers, which is why we have this notation, so we don't have to write all this. Remember laziness? The set of all natural numbers is closed under addition. Now, the set of all natural numbers is not closed under subtraction. And that's important at any 2, right? So I'm going to write n here, which is the same as the set of all natural numbers is not closed under subtraction. Oh, and there is one more word that I mentioned, but I didn't write, closure. Closure. So n is not closed under subtraction, which means actually mathematicians like closure. They really do, because that means the result exists within the set we are looking at. So name another operation that n is closed under. So find another operation that the set of all natural numbers is closed under.
Multiplication.
Very good. there is this recurring theme that addition, multiplication good, division, subtraction bad. They have bad properties. So n is closed under multiplication, and not closed under division. And closure is a big motivator. So imagine that we do the following. Trying to make the so imagine we play the following game. Here is the set of all natural numbers. 1, 2, 3, 140, 2021. They just keep going. Infinitely many, right? And now imagine that this is going to be an expansion. So we're going to keep this and try to keep all the rules that we discovered. For example, that addition is commutative, the 2 plus 3 and 3 plus 2, same thing. And we're going to do the following. We're going to grab any two natural numbers and we're going to subtract. We're going to do things like 10 minus 3. Well, 10 minus 3 is 7. That's in the set. But we're also gonna do 3 minus 10. Now 3 minus 10 is not in the set. So we're gonna make up a symbol for it. The symbol that we made up for the result of 3 minus 10 is negative 7. And we're gonna throw it in. So if the subtraction results within the set, cool. If not, we're gonna create a symbol for that. So for example, 5 minus, I'm sorry?
Can I ask a question? Can I assume that all natural numbers are positive numbers?
Yes, exactly. It's just even the word positive doesn't make much sense unless you already have negative. Exactly. But the positive integers, oops, I just said it, integers will be what we're gonna get. If we put in 3 minus 3, the result of 3 minus 3 is 0. And so what we're gonna get here is the opposite of all natural numbers, and 0. And so when we throw in all the possible results that are not there, we artificially create a closed set. This set here is not closed under subtraction. Well, of course, we would have to worry about the subtraction between these two guys, but this set is called a set of all integers. And so there are negative integers like negative 7, and there are positive integers, which is the same thing as natural numbers. And so this is called a set of all integers. Now, in mathematics, we like to double part of the letters. And if you think about integer, the word integer starts with an I. That's not a good idea to double it because it looks like 1 numeral 2. So mathematicians were in trouble. They went to the word number, but it starts with the same letter as natural. But actually, mathematics is crawling in Germans. There are so many Germans who were like fast, amazing mathematicians. So what we did for the word number in German, which starts with a Zahl. You don't have to know this. This is the German word Zahl for numbers. So it's capital Z, and then you double this part is the set of all integers. So the set of all integers. And now the set of all integers are closed under what? Let's go through the 4 basic operations. Is the set of all integers closed under addition? So the sum of any 2 integers, is that again an integer?
Yeah.
Yes. Subtraction?
No, it's not closed.
No, give me an example.
Yes, it is closed.
It is closed. It's, you know, that's funny because if I say convince me, if the answer is no, that's much easier because you just give one example. If the answer is yes, then it's much harder, but the answer is yes. Any 2 integers, if you subtract, the result will be an integer. Positive or negative, but an integer. So Z, the set of all integers, is Say it. Minus
3 minus 2.
3 minus 6. That's negative.
2.
That's, sorry.
Oh, I said 3 minus 2.
Well, that's negative 5. That is in the set. So Z is closed under. I mean, this set is bigger. This have every negative integer there. Negative 92. I'm just gonna have to stop because there are infinitely many. So we just try to indicate. Usually the dot dot dot.
Okay.
Z is closed under addition, subtraction, and well, there are two other operations.
Multiplication
Very
and
good.
division.
Right. Oh, but division misbehaves, right?
Exactly.
So the smallest set that is closed under is called a closure. So we can say that the set of all integers is the closure of the natural numbers under subtraction. As the smallest set containing the natural numbers that is now closed under subtraction. So the integers are better because now we have closure under subtraction, but division does not work yet, right? 10 divided by 2, yeah. But 2 divided by 10, no. So Z is not closed under division. So I think now that closure under operations is the driving force beyond these expansions of our number system. So guess what we're gonna do to fix division?
When you say fix it, you mean to open. I mean to close it, correct?
Right. So we're gonna have to create a bigger set. We're gonna keep everything here and not just the numbers but the rules, and we're gonna throw in extra numbers so that that bigger number set would be closed under division, which goes like this. If it's 10 by 2, 5 is in the set, we're cool. But if it's 2 divided by 10, we have to come up with a symbol or a concept for that. So guess what did we throw in to fix division, the last operation to be fixed, to be foreclosure? Well, what is 2 divided by 10? The result of that, what is that?
5.
No, that's 10 divided by 2, but thank you for talking to me. 2 divided by 10.
Negative 0.5, isn't it?
No, that fractions and decimals, but decimals are fractions. So that's a fraction, right?
0.
So what we're gonna do is we're gonna throw in, so we're gonna grab every pair of integers and we're gonna perform a division. And if the result, quotient, the result of a division is called a quotient. If the quotient is an integer, we celebrate. If not, we come up with something like 1/5 would be the result of the division 1 divided by 5, whatever that is. 3/7. How about -3/7? So we throw in all these numbers that are a result of a division between two integers and not yet in the set. And that's bigger set. And we try to keep not the rules too. That bigger set, does anyone know what that set is called? Oops, it doesn't even show. Wait.
Real numbers?
No, not yet. That's the next one. I don't know why it's doing that.
Negative numbers.
Oh no, the negative numbers we already had. All right,
Okay.
let me first write, but thank you so much for talking to me. That's the most important. So let me write down the definition. Oh, so it's called rational numbers. So a number is rational. A number is rational if it can be written as a fraction of two integers. Now I left a gap here. So if you can write a number integer divided by integer, that's a rational number. Now I already told you what is the fancy name for result of a division. What's the fancy word for that? Result of division.
Quotient.
Quotient. So I'm going to write quotient, fraction, proportion, ratio. Those all would work, but I'm writing quotient because that will give you a clue how we labeled. The set of all rational numbers is for quotients of integers. So Q is the set of all rational numbers. Now, if you look at the picture, we expanded the word, so we kept everything. So everything inside this orange rectangle should be a rational number. So why would 3 be a rational number? Always go back to the definition. A number is rational if we can write it as an integer over an integer. Can we write 3? Yeah, go ahead.
Oh, no. I didn't see that.
Because we can write it by 9 divided by 3.
Exactly. Or 3 over 1 is the simplest, 6 over 2. It doesn't have to be the simplest. If you can come up with two integers that they divide to 3, 3 is an integer. So it's all about the definition.
I got a question. So that
Yes.
number is rational only when it can be written as a quotient of two integers.
Exactly.
Quotient being the top number.
No, that's the numerator. Quotient is the result of a division. So
Okay.
I misspelled it, by the way. Quotient is a result of a division. Result of a division. And no remainder. So for example, 1.5. That's not an integer. Can we write 1.5 as an integer divided by an integer?
No. Origin.
So is 1.5 rational?
Yes.
Convince me.
No.
I suggest because this is a decimal, but if we convert it to fraction.
Yeah, but that's you're using stuff that's in our future, not much, to 20 minutes in our future. So go back to the definition. Come up with a pair of numbers. That's the only way you can convince me.
So no, it's not a rational number because it's a decimal.
Yeah, it is 3 over 2, right? 3 divided by 2.
Okay.
Right?
Oh, okay. Okay.
Right, so we have much more numbers than just the integers, right? 2 over 7, that's a hideous decimal. 2 over 7, that's quite yucky. So we have all kinds of, now decimal is just a form of presentation, like 1.5 is 3 over 2. Now there is just one concept, the number, and these are different forms of the same thing. Think of it as outfits. So this is fraction form, this is decimal form. And here it's either way, but for example, 2 over 7, much more prefer to write it as a fraction because as a decimal, it's pretty awful. Now, before we go back to this one, let me show you something that cannot be fixed. So let me write down another way to write. This is going to be an eclectic page. Page 5. So we can say A over B. This little braces make it a set. Whatever is between two braces, it's a set. Now the column means such that, and then we're going to say A, B integers, and B cannot be 0. So we cannot divide by 0. Let me weave through that real quickly. So let's look at 0 over 3. And so division has to do, division is defined in terms of the multiplication backwards. So 20 over 4 is 5 because times what is what?
Because 4 times 5 is 20.
Mm-hmm. And then that's good. Start with the division and the multiplication backwards with something you know well. And then let's see these two, because visually they're similar, but they're very, very different. So let's try to do these two division by, what do I put here so the multiplication backwards should work? So you see these two have to be multiplied. So 3 times what will give you 0?
0.
Exactly.
Anything
Yeah.
times 0.
Exactly. And if you say 0 divided by 3 is 0. So the answer here is 0. Now this, however, is a very different game, because 0 times what will be 3? You just said any number
3.
we put in here, it's not going to happen. You can write here.
Anything 0 is going to be
It's
0.
an irrational number.
No, this doesn't even exist. It's undefined. That cannot even be fixed. And it's
Irrational number.
no. It's not a number. We can't fix this by throwing in new numbers. We just cannot fix it.
Okay.
So
Is
this
it because of that 0?
No, it's because the multiplication backwards will never work. If you want to put a fixed number here, you can put gazillions. That 0 is going to slam it down to 0. 0 times nothing will give you 3, right? So, and so let's ask the calculator. 3 divided by 0.
It's error by 0.
Yeah, and that's a nice calculator. Sometimes you will see some weird stuff like domain error, and domain has to do with a number is not coming out of. You're putting in a number that cannot be meaningfully come out of the operation. So this one we say undefined. Undefined. And then, you know, mathematicians are very thorough. So one mathematician could say, okay, let's not divide by 0 ever. But then someone says, wait a minute, what about 0 over 0? Maybe that would work. What do you think about, given the definition of with respect to the multiplication backwards?
Defined.
Could be any number.
Now that's the problem. Not everything will work, right? Mathematicians did not like an operation that yields for, instead of a result, it yields for every number. That's crazy too. So we said, you know what, let's just say, actually, this used to be called indeterminate because everything would work, but now we just call it undefined. Okay. So the first commandment of mathematics is thou shalt not divide by 0, ever. That's the most offensive mistake, is division by 0, as I found out. And sometimes you do that. For example, we'll come back here. X squared equals 4x. Now we know how to solve this, right? You subtract, factor, and apply the 0 product rule. Right? So we have 0 and 4, right? But some people would say x squared equals 4x. They both are divisible by x. I want to divide by x, and don't try this because this is bad. Now, what solution did you lose? Well, did I lose? We lost 0. Why? Because we divided by 0, right? So sometimes it's not so, yeah? So
No, I'm sorry. Turn my mic off.
Bad. Don't ever do that. So if you feel like now there is a careful way to divide by an unknown. You have to consider, what if it's 0, and if it's not 0, then I divide by it. Then you would get the right answer. But at this point, you don't need to divide by the unknown. There will be a point when we will be forced to, and then you have to separate the universe into 2 possibilities. If it's 0, we're not dividing by it, but we check. And if it's not 0, we divide by it. So this is an example of division by 0 when it's not that obvious that we're dividing by 0. Okay, so So division by 0 cannot be fixed, but otherwise, the set of all rational numbers is closed under. Now think of a rational number as an integer or a fraction. And now let's ask, what about addition? If you add, well, actually, integer or fraction, you can always think of it as a fraction because 3, you can think of it as a fraction as 3 over 1. So if you add 2 fractions, is the result always a fraction or an integer? And then what about subtraction? Sorry, go ahead.
Repeat the question.
I said technically it's always a fraction because it's always over 1 if it's a whole number, right?
If it's an integer, exactly. And by the way, whole number, I'm glad you mentioned it. Whole number is the natural numbers plus throw in 0. Yeah, so the sum of 2 rational numbers is a rational number. Same with the difference. And the product of 2 rational numbers is a rational number, and the quotient is 2. So this here is the smallest set containing the natural numbers that is closed under the 4 basic operation. We could say that it's the closure of the natural numbers. All 4 basic operations. Okay. Now, I have some bad news. There are numbers so weird that you cannot write them as the quotient of 2 integers, which is an outrageous property because there are so many integers to choose from. Can anyone name a famous number that's famous for not being rational, also called irrational?
Number P.
Say that again.
The
Oh,
pi?
pi. Yes,
Pi?
very good.
Yeah,
Pi. Pi is a menace. That's really bad. There is another one I was hoping you would say. Square root of 2. Square root of 2 and pi are famous irrational numbers, but pi is so much worse than square root of 2 because you can square root of 2 and you're back to normal, but pi, you can square it, you can raise it to any power. It's not gonna come back to integers. So let's look at, if I find it, the definition of a rational number. So a number is rational if it can be written as a quotient of 2 integers. A number is irrational if, and all you have to do is put the word not strategically in here. So a number is irrational if it cannot be written as a quotient of 2 integers. And I have bad news, such outrageous numbers exist. So a number is irrational if it cannot be written as a quotient of 2 integers. Oops. Go away, kitty. Not yet. Sorry. Kitty, go away. Oh, sweet. Go. All right. So I remember my outrage that such numbers should exist. But square root of 2 and pi are famous examples. Now you might say, wait a minute, we have closure under all 4 operations. Why would we need even more numbers? Why would we need irrational numbers? And so let me ask you, where does pi coming from? What were you studying when you were looking at pi?
A circle.
Exactly, we were dealing with geometry. And so we could have just lived with rational numbers, but here is the problem. There is one thing to say this is distinct, it's called distinct objects, that this is 1, 2, 3. It's a whole other game is when you want to put a number on a distance. You say, I want to call this distance 1. And then, of course, if I double this distance, I want to call it 2. That's different than counting objects, because if you call this 1, now this length here, this should be a circle, is going to be an irrational number. It's going to be, if the radius 1, it's twice pi. By the way, pi, there is a pi button on your calculator. It's right here, and that's much more precise than if you punch in stuff. Use the pi button. So this would be twice this, so 6 and change. And if you remember the Pythagorean theorem, if not, don't worry, because we're going to cover it. If you make a square with sides 1 and 1, now this length here is going to be forced to be square root of 2. So what took us to this mess, well, we would have come up with square root of 2, because it's so easy to say I multiply a number by itself, I get 2. So that's not far from rational. But pi, we would never have bumped into pi without wanting to put numbers on distances. That's a whole different ballgame. So, and the fact that pi is irrational, okay, so it's kind of funny. It's the second time in this class that to prove an answer depends on the answer. To prove that a number is rational is quite easy. Well, here it is, 3 and 2, divide, you get 1.5. Therefore, this number is rational. Now, proving that something is irrational is harder because, well, what does it mean, irrational? It means you cannot write it as a quotient of 2 integers, right? Well, if you say, well, I tried for hours, but I couldn't, that's not going to cut it, because what if you just tried 5 more minutes and you bumped into it, right? Somehow we have to show that no 2 numbers, if you divide, will give you square root of 2. And that's a much harder undertaking. You're going to have to wait until calculus 2 to prove that pi is irrational. I could show it to you today, that square root of 2 is irrational. That's a much easier proof. Maybe we'll make time and I'll do that. Maybe I'll make a video, something like that. Okay. So now let me repeat the little picture. So once upon a time, we started with the natural numbers, small, cute little set. And then we found that the natural numbers is not closed under subtraction. So we fixed that by throwing in other numbers like 0, -1, -2. And now we got the set of all integers, which was closed under addition, subtraction, and multiplication, but not under division. So we threw in new numbers, sort of formal results of division of integers, and we got the set of all rational numbers. And then someone said, oh, I want to put numbers on distances. And now we threw in all the numbers. And so what I want to, the reason I'm drawing a new picture is I want to sort of give you the idea. This here, there is no separate notation for it. This is the irrational number. So square root of 2 and pi comes here. And look at this, and together the rationals and the irrationals form the real numbers. So this here is the real set of all real numbers. Now, with the sizes, I wanted to give you the idea that not only these crazy numbers exist, actually there is more of them than rational ones. How about that? There's more hideous numbers that you cannot write as a fraction of 2 integers than those nice, decent integers or quotients of integers. That's pretty wacky.
7.
Say it again.
7, the number 7.
Oh, natural. It's right here.
No, I say right. Doesn't matter. Never mind.
Square root of 7 is irrational. You're right. You put an integer under a square root, and if it's not a perfect square, like 9 or 16, then it's irrational. There's no in between. Like, oh, if this square root is not an integer, but at least a fraction, that never happens.
Okay.
And remember that what got us into the irrational numbers was the idea of distances, visual things as to put numbers on it, so the real numbers fill up the number line. And that's a marriage between algebra and geometry in a way. 0, 1, 2, -1. So the rational numbers don't fill up the number line. The real numbers do. So for every point, there is a number, and for every number, there is a point. And that's the real line, the real number line. And so there is this marriage between algebra and geometry, right? Line is a thing from geometry and number is a thing from algebra. And this is where this connection starts, and it's going to be a very important connection for us. So the numbers are rational and irrational. And so this is our number system. Now you could say, okay, what about next? Is there a yet bigger number system? And the answer is yes. Someone said, okay, well, what about square root of -9? If you take 3, that squares to +9. If you take -3, that too squares to +9. So it looks like no real number squares to -9. Indeed, square root of -9 among the real numbers is undefined. But some people say wanted to have negative numbers to have square roots. And we expanded this number set to even a bigger one. Now I would have to use the room as the size. That number system is called the complex numbers. And within the complex numbers, negative numbers have square roots. And then you could say, okay, what about next? What's bigger? And then there are two answers to that. First of all, there is no operation that cannot be settled under the complex numbers, which we will study. The complex numbers is closed under anything you can think of. So there is no new operation that would motivate us to open up, expand it further, and would have a bigger number system. But mathematicians are kind of curious, so they say, okay, maybe there is no motivation, but I'm just curious. So as it happens, there are several ways to go beyond the complex numbers. I know of at least 2 of them, but we lose huge chunks of mathematics. Basically, this is complex numbers is the end of the road when it comes to keeping all of our rules. So that's going to be the last step. It's sort of the wall. Yes?
Professor, I got a question. So what are these numbers used for in the real world?
Oh, complex numbers?
Yeah.
Well, you know, complex numbers, somehow the word imaginary slipped in, that it have a real part and imaginary part. But if you think about it, even negative numbers are kind of weird. Where do we use negative number? Depth, negative temperature, negative height, right? So we kind of use that. Where do we use fractions? You know, now I know it was closure under division, but when I was a kid, I thought it's about splitting candy with brothers and sisters. You know, that's why we have fractions. Complex numbers are fascinating. The complex numbers teach us about real numbers. So there are rules about real numbers that I'm going to show you. We wouldn't know without the help of the complex numbers. The thing is that if you look at mathematicians working on open questions, very few of them are working on numbers because that's pretty much settled. Even though the complex numbers is so huge, it includes the real numbers several times, but they are not very mysterious. You know what is the most mysterious number set? The one with the most open questions? It's this cute little one, natural numbers. We still have the most open questions on those. So complex numbers are also used in part of electricity. So if you Google complex numbers in electricity, there is one impedance, I think it's called. There is one part of physics where the math can be only described using complex numbers. And then there are other questions, puzzle sort of questions. If you ask, okay, here is the number 2021. How can I write it as a sum of 2 squares? That may not be very practical, but it's a question about real numbers, well, integers, that actually complex numbers helps us. So sometimes complex numbers help us to solve questions of practical nature about the natural numbers. So that's what I had for answer. And by the way, I like your question. Like the question. Any other questions? All right, so today I wanted to do something fun. So let's first, let me ask you this. What about 0.12? Is that a natural number? Rational. It's not a natural. By the way, this is it is? Convince me.
It's 12/10.
Love it.
100.
100. Okay. Yes, 12/100. Very good. 12/100. Very good. 12/100. Very good. So let me show you one generic way to do this. So we want to prove that 0.12 can be written as a quotient of two integers. Well, let's break down into two projects. Let's first write it as a fraction. So this is what I call growing of 1. You can look at this as division and fraction. You can always look at a fraction as a division and the division as a fraction. And you can play them off against each other. Two are equal because you divide by 1. Well, just think about it in terms of the multiplication backwards, right? 1 times 0.12 is going to be 0.12. So now that it's a fraction, I'm going to exploit a fraction's fundamental property is that you're not changing the value if you multiply upstairs and downstairs by the same number, right? When you bring two fractions to the common denominator, or when you simplify a fraction. So we're going to multiply upstairs and downstairs of this fraction so that the goal is to fix it, so that because this is not an integer. It's a fraction, but it's not a fraction of two integers. So what number would you want to multiply this so that after multiplication, it's an integer? I'd go with 100, right? If we multiply this number by 100, we get 12, right? Multiplying by a 10 power is a matter of moving the decimal point, right? But now we kind of made a commitment. If we don't want to change the value of this fraction, we have to multiply the denominator by the same thing. And in this case, you never have to reduce the fraction because the question is it rational? Which means, can we find two integers? You don't have to find the best ones. You don't have to show its simplified form. Just 12 is an integer, 100 is an integer, check, check, rational. And then you can check the calculator that 12 divided by 100. Oops, I divided by 0. Oops, don't do that. Shaky hand, sorry. 12 divided by 100. There it is. See? Okay. So what about, and I'm going to stop soon because you guys got the idea, 2.021. Did you all sign in? There's lots of people still in the room. Please sign in if you haven't done so.
2021
Divided by?
divided by 1,000.
Bingo. So we grow a 1, and then we're going to have to move the decimal place 1, 2, 3 times. That's 3 zeros after the 1, so 1,000. We multiply upstairs and downstairs by 1,000, and there it is, and we can check. 2021, my 1 is sticky, divided by 1,000. Yeah, all right. So now I'm gonna write down a statement and see how you feel about it, true or false. Every terminating decimal all right, so here is what I wrote. Every terminating decimal represents a rational number, where terminating means there is a last digit, it ends. Like 0.12 and 2.021, those are terminating decimals. How do you feel? Do you feel that this statement is true? You feel kind of convinced? Or do you think this is
No.
false? Yeah, go ahead.
I think it's false.
I think it's true.
Actually, it's true because you grow a 1, and then if it's a terminating decimal, then a suitable 10 power will move the decimal point to the end. So if it's a terminating decimal, you can write it as an integer over a 10 power. It might be a million digits long, but it can be done. So this is a true statement. So this is true.
Okay.
But notice that the decimal is not someone, it's more like a presentation of a number. So this number has 3 representations. This is what we call an improper fraction. This is what we call a mixed numbers, and this is a decimal. But it's one number, one rational number that has these 3 presentations. Okay. Now, not backwards, because not every rational number, if you write it as a decimal, is going to terminate. Can you come up with an example of a rational number that's not a nice decimal? Well, what would 1/3 look like as a decimal? 1/3.
Would be 0.3333.
Right. Yeah, and those you just said 3, but I know what you meant. So 1 divided by 3, it looks like this. Now the calculator shows maybe 12 digits. It remembers maybe 15, but we're talking infinitely many, right? Because if we write 1 as 1.000, it's a little bit of a claustrophobic experience. Let's do, this is long division in this country. I think it's presented like this. So 3 goes into 1, not at all. But 3 goes into 10 3 times, because 3 times 3 is 9. We write down that quotient, we subtract. 10 minus 9 is 1. Bring down the 0 again. 10 divided by 3 is 3. 3 times 3 is 9. We subtract. 10 minus 9 is 1. You see, it's kind of a claustrophobic experience. We're just going to loop. It just goes on and on and on and on. So backwards, it's not true. Not every rational is terminating. But if a decimal terminates, that's rational. Now, 1/3 is not 0.3. It's 0.333333, right? This here is actually 3/10, right? So 1/3 is the first argument against decimals and in favor of fractions. Because as decimal, well, this is one way of denoting it. And there is another notation where you draw a little bar over the repeating part. This here is 1/3. If you if you have a number like 1/3, that's already gently pushes you towards fractions as opposed to decimals. Let's look at 2/7, because 2/7 is really hideous. All right, ready? It won't hurt. The calculator will do the same thing. All right, let's get ready. 7 goes into 2, not at all, right? All right, what about 20? Yeah, in my country, we had to do little tick marks. You guys don't, but 20 divided by 7.
2.
2, very good, because 2 times 7 is 14. We write it down and subtract. 20 minus 14, that's 6. And now we bring down the next 0, 60 divided by 7.
8. 7 times 8.
8 times 7 is 56. Very good. 8 times 7 is 56. We subtract. Bring down the next 0. 40 divided by 7.
I'm gonna put
10,
5.
5.
Put 5. I'm gonna put 35.
5, because 5 times 7 is 35. We subtract. We get 5. We bring down the next 0. Usually we hope for no remainder, but as long as there is remainder, we just bring down a new 0. 50 divided by 7.
6.
7.
7.
7, because 7 times 7 is 49. We subtract 1, bring down the 0. 10 divided by 7.
1.
1.
1. 1 times 7 is 7. Subtract 3, bring down the 0. 30. 30 divided by 7.
4 times
Gotta put
7.
4. 4.
4.
4.
Thank you for talking to me. 4 times, being wrong is okay, not trying is not okay. 4 times 7 is 28. Subtract 2, bring down the 0. 20.
20. Gonna put 2 again.
2.
2, because 2 times 7 is 14. Subtract, we get 6, bring down the 0. 60 divided by 7.
8.
8. 56.
Right, I usually do it until the class starts to beg to stop, because it's going to be
See
the
a
same.
pattern.
Right. Now we're stuck. We always bring down the same zero. So this is going to repeat.
Yeah.
So
Oh, so it doesn't stop.
2/7 looks like it's not a repeat. No, it's never going to stop. It's never
It's
going
a
to stop.
terminating number.
No, it's a repeating one, like 1/3. But the repeating block is 6 digits long. It's 0.285,714, 285,714. If you punch it into the calculator, it looks like, you know, that 57 rounds up to 60.
Right.
But it is a repeating decimal of a 6-digit long repeating block. So now now we know. Oh, so now. Okay, so we almost ran out of time, but I'm dying to show you this. So we'll start with here, but I think we can cover it really quickly. This is the fun stuff. If you have a decimal that doesn't terminate, but it repeats, that too is a rational number. And I'm going to show you how to convert it back to a fraction. So suppose we have something like 0.77777. So this is the original number, and the problem is going to say the following. Prove that this number is rational by expressing it as a quotient of 2 integers. You never have to reduce it, by the way. So the first thing we're going to do is we're going to drop this notation and we write it like this. Now, visually, you see 4 times the digit 7, but mentally or theoretically, how many are there here? Infinite, right?
Infinite, yeah.
Okay, so now this is a very strange equation. So we're going to do 2 strange things. Number 1, we're going to multiply both sides of this strange equation by 10. So, and number 2, I'm going to write it above instead of below. 10 times x is 10x. And what happens to a decimal when we multiply it by 10? You just move the decimal point, right? So we're going to get 7.7777, right?
Right.
So far,
Right.
everyone is on page. Oh, this is fun stuff.
Yeah.
So here is what we're going to do. We're going to use the number's own badness against itself. We're going to subtract the 2. 10x minus 1x is just 9x, right? But now look at the decimal. There is infinitely many 7s, under which there is a 7, 7, 7, 7, 7. Chop, chop. I call it chop, chop because we cut off the infinite tail of this number. What we get is just 7. Right? It's a subtraction.
Uh-huh.
And now look at this equation. 9x equals to 7. Solve for x.
X is 7 on top
Over
of
9. And my favorite part, check, check, check. 7 divided by 9. Now, this 8 is rounding. It rounds up 77. You're much smarter than your calculator. The calculator doesn't understand infinity. It just knows rounding. So it rounds 77 up to 80. But our answer is correct. Kind of cool, isn't it? It's called, I call it the chop chop game. So now the repeating block doesn't always this simple. For example, you saw 2/7 has a 6-digit long. Let's look at something like I don't know 0.464646. Okay. So if we multiply this by 10, that's not going to help us because then what we were going to get, I want to write it with pencil so I can erase it. Pencil, my country for a pencil, that works. You see the problem here?
Yes.
That's not going to help us, right?
Right.
We want a 4 over, now we're just creating another infinite tail, if it's even meaningful. So what should we do? What number would work to multiply both sides by?
46.
No, it's going to be a 10 power. It's just not 10 because we want a 4 over a 4.
Oh, I see what you mean.
And a 6 over a
100?
6. 100 will work. And that's the simplest
100.
right? We shift by
'Cause
an entire block, basically. Exactly. So
You're
then,
moving the decimal 2 places.
exactly. Now, with your finger, you can figure it out, but because of the subtraction, you want to align it, and you don't just want to fake it, you actually want to do it. So after a multiplication by 100, we're going to get 46.4646. So we're going to, so the 6 comes over the 0, and then there it is, 464646. And also, I just mentioned in passing that it's a false statement if you don't do the ... Because terminating decimals don't just produce an extra block just because you need it. It's infinity that is so strange. Infinity has a strange property here. So now what do we get after the subtraction? Here we're going to get 1x subtracted from 100x is 99x.
99.
And then we managed to chop it down to 46. And so x is 46 divided by 99, my favorite part. 46 divided by 99. There it is, and the 5 at the end is because 46 was rounded up to 50. So it's correct. So let me write down this statement. Every repeating decimal represents a rational number. What do you think, true or false?
True.
It is true. So if a decimal doesn't ever end, but at least it repeats, that too is a rational number. So this is proven, but you kind of see why. There is if it repeats the length of the repeating block, that's how many 0 you shove after a 1, and then you do the chop game with that 10 power. So this is a theorem actually. Theorem means it can be proved. Stop the numbering. Okay, 7, 8, 9, 10. So one thing that I'd like to say, not all of them are so nice. You could just say, oh, it's always over 9 or over 99. It's going to be a little bit complicated. I'm going to post the handout, and there are videos. I want you to look at it, even though we didn't finish it in class, but there are the videos and everything. So they're not always like, oh, why don't you just, so don't try to do it in your head. I don't have formulas, I have methods. So try to practice this method, because there is a type of an example that I didn't show you that is more complicated. But now, before we go, what about the decimal presentation of an irrational number? What do you think? Every terminating decimal represents a rational number. So irrational numbers cannot be terminating as decimals, right? Because if it's a terminating decimal, we prove that that's a rational number. Well, we convinced ourselves. So an irrational number as a decimal cannot be ending. It has to be an infinite decimal. Can it repeat?
Yes.
No,
You mean
that
in order
too
to
would
be
make
an
it rational.
irrational?
Right, so there is not much left for irrational numbers, right? A terminating and a repeating decimal, those are all rational. So a number, if it wants to be irrational as a decimal, it cannot stop and it cannot repeat. That's terrible. That's really, really bad. And we basically, with these two terms, we discussed how irrational numbers look like. They're bad. They don't end, they don't terminate, and they don't repeat either. So this is why on our next class, we're going to start reviewing from Algebra 2, but this is a crown achievement of Algebra 2, how to manipulate with symbolic objects like square root of 2. Because we cannot write them as a decimal, and we cannot write down as a fraction either by definition. You know, there is no two integers that would divide to that. So that's why there is going to be these radical expressions that we're going to invite permanently into our symbolic algebra. And that's what we're going to do next class. So Oh, I ended. Oh no, actually there is 5 more minutes, right? Is it 45 or is it? There is 5 more minutes. Aha. I'm sorry, my other class on Tuesday, Thursday, I think they end at 45. So let me show you an example that's a little stickier. All right, so let's do this one. 0.001 39393939. Okay. So by the way, it's not that students don't know how to do this. It's just very important that you do what I'm asking you to do and not something else. You see, this number here is 0.391391139. This number here is 0.1 39393939. And this number here is 0.1399999. Got it? So it's just the repeating block that is overlined. And it doesn't have to, the repeating doesn't have to kick in all at once. There is some stuff happens before that kicks in. And by the way, several methods on the internet, if you choose me, you're gonna see the method I'm showing you. Everyone else does something else. I don't care, just get it right. In some way, that other method is more elegant, but I have my weird, evil reasons to show you this one. All right, so the first question is, what should we multiply both sides by?
By the 3. Oh, I'm sorry. 1, 2.
And so this is the funny thing is, this 3, you wanna promote it by 2. It doesn't matter what happens at the beginning. All you have to ask yourself is how long is my repeating block? That's the only thing that matters here. How long is our repeating block? How many digits long?
It's 2 numbers.
It's 2. That means
2
100
digits.
will do, right? Because if you look at, because you want to promote this guy here. So we're going to multiply both sides by 100. I'm already messing up because. So we're going to multiply.
1,000, correct?
No, it's the number of decimals you want to move is the number of zeros after the 1. And it's not the beginning. Just look at the infinite end, the tail that matters. And that's kind of the point. We're not going to get an integer after the chop game. We're going to get a terminating decimal, which is easy to fix. So if we multiply this by 100, we're going to get 0.1393939. And it looks like magical, but just think about it from the point of view of 1 single digit at the end. This will move 2 decimals. It will be promoted by 2 decimals if you multiply it by 100. So now after the subtraction, we get 99x equals to, and this is why I said don't just fake it, really align it. 9 minus 9, oh, here is the first one. You see? So we have 0.1, this is a 9. So 9 minus 1 is 8, 3 minus 0 is 3, 1 minus 0 is, so we got 0.138 and 99 here. So at this point, because we want 2 integers, that's an easy fix. Now we're gonna multiply both sides by another 10 power. But now the goal is to fix this terminating decimal. We want it to be an integer. So what should we multiply both sides by?
1,000.
Yes, 1,000 will work. So if you multiply, sorry, my cat thinks class is over. No, it's just 1 more minute. So if you multiply both sides by 1,000, we're gonna get 138 here, 99,000 on the other side. And then we divide, and so 138, and you never have to worry about simplifying it. You can do 0.13 over 99, but then you still have to fix, and now upstairs and downstairs has to be multiplied by at least 1,000. So sooner or later, you have to come up with that 1,000. And there it is. Solve for x, and here is my favorite part. Let's check. Oh, don't die on me. Okay. So what do we have? 138 divided by 99,000. There it is. Now 93 was rounded down to 90, so it didn't show a 4. So this is kind of the worst case scenario when there are two things to do. First, you chop off the infinite tail, that's the hard part, and then you might land on a or a terminating decimal. But that's an easy fix. You have been very patient with me. Thank you for waiting. Sorry keeping you beyond the time. Thank you guys. I hope I'll see you on Wednesday. Great class. I enjoyed it.